Hi everyone, my name is Madhav. Today my topic is about relationship between matrix functions. First, first coming to the introduction. The Laplace transform plays an important role in control theory. It appears in the description of linear time invariant systems, where it changes convolution operators into multiplication operators and allows to define the transfer function of a system. The properties of systems can be then translated into particles of the transfer function. In particular, causality implies that the transfer function must be analytic in a right half plane. This will be explained in section 2, and a good reference for these preliminary properties and for a panel of concrete examples. The important notion of stability is then introduced in section 3. We shall see that several kind of stability with different physical meaning can be considered in connection with some function spaces. The Hardy spaces of the half-plane, these function spaces provide with their norms a measure of the distance between transfer functions. These allow to translate into well-posed mathematical problems. Some important topics in control theory. As example, the notion of robustness. A design is robust if it works not only for the postulated model but also for neighboring models. We may interpret closeness of models as closeness of transfer of functions. And then now coming to the linear time invariant systems and their transverse functions. Linear time interval linear time invariant system plays a fundamental role in signal and system analysis. Many physical processes possess these particles and even for nonlinear systems. Linear approximations can be used for the analysis of small derivation for an equilibrium. In addition, LTI systems can be analyzed in details, providing both insight into their properties and a set of powerful tools that that form the core of the signal and the system analysis. A continuous time system is an input output map u of t to y of t. For, for an input signal u or to c, output signal y is to or to cp. It will be called linear if the map is linear and the time invariant in if which is linear and the time invariant if a time shift in the input signal results in an identical time shift output signal. A linear time invariant system can be represented by a convolution integral. Here we can see convolution integral y of t equals to integral minus infinity to infinity into h into t minus t into u into t of dt. T of dt integral minus infinity to t infinity to infinity h of t into u into t minus t dt. Assuming that the integrals converges, the responses to e power st is the form of is of the form y of t equals to h of s e into st, where h of s is the Laplace transform and defined by h of s integral minus infinity to infinity h of t into e power minus st by dt. In the specific case in which r of s equals to 0, the input is a complex integral e into I omega t at frequency omega and
h of I omega viewed as a function of omega is known as frequency of response of the system and is given by the Fourier transform h of I omega integral minus infinity to plus infinity h of t into a into I omega t dt. In practice, point-wise measurements of the frequency response are often available. Of the classical problem of harmonic identification consists in finding a model for the system which produces the data well enough. The Laplace transform of a scalar function f of s L into f of s into equals to integral minus infinity to infinity e power minus st f of t dt. And the third one way, function spaces and the stability. Sorry, here small change. Function space and the function spaces and stability. An undesirable feature of a physical device is instability. In this section, we translate this into a statement about transfer function. A stable system is one in which small inputs lead to responses that do not diverge. To give a mathematical statement, we need a measure of the size of a signal. The most natural measure is the L infinity norm. A signal will be called bounded if there is some m greater than 0 such that magnitude of u into infinity equals to sub of u of t less than m t greater than 0, where two double slashes denotes the Euclidean norm of a vector. We will still denote L of infinity the space of bounded signals omitting to mention vectorial dimension. We may also be interested in the energy of a section which is given by the integral magnitude of u2 square infinity to 0 u of t into u of t dt. U of t u2 is to y of t equals to h into u of t. Hard spaces of the half plane. Here we will see hard spaces for the half plane. The hard space HP is defined to be the space of functions f of s analytic in the right half place which satisfy f of p sub 0 to x to infinity minus infinity to plus infinity f into x plus I y p into dy 1p less than infinity exists on the imaginary axis. We may identify f belongs to h power p with f naught ir. Some notations of the stability BIPO. It can be provided that the system is stable if and only if the impulse response is integrable over 0 comma infinity if needed. If f of h of t is integrable u of infinity less than m, then y of t equals to less than or equal to m integral 0 to minus t magnitude of h of t minus t of dt, that is equals to m into integral 0 to t h of t dt. Finite order of LTI systems. Among LTI systems of particular interest are the systems governed by the differential equations x of t equals to axt plus bu of t, y of t equals to cxt plus du of t, where a b c d are the constant complex matrices of type n into m into m, p into n, p into m. Assuming x equals to 0, the solution is x of t equals to t to 0 into t minus y of t equals to 0. H of t equals to c a t b plus d delta naught, where delta naught is the delta function at 0. Thus h is a generalized function. L square norm approximation. In this case of the L square norm, An explicit solution of the model reduction problem cannot be computed. However, the L-square norm being differentiable, we may think of using a gradient flow method. The mainly difficulty in this problem is to describe the set of approximations, that is rational stable functions of a degree n. The approaches that can be found in the literature differ from the choice of a parameterization to describe this set of approximations. They often run into difficulties since smoothness can be lost or understandable method. Where q is the inner point of the function, q belongs to g into g of q of 2. Thank you.